Let me remind you, we defined Mn, which was a maximum of SV. And then the basic theorem that we are after is the expectation of Mn is nx star minus 3 over 2 x star log n plus order of 1. So this is a theorem that we are after. And we saw that once we have proved that, then we will know that the fluctuations of the maximum are of order 1. This we saw last time. Okay, so there will be 3 steps for the proof. So first we will get a lower bound for the right tail. Namely, we were going to show something like the probability. So if we call this quantity here alpha n, we are going to show that the probability is that Mn is larger than alpha n plus y is greater than a constant e to the minus x star y for some constant c and y positive. Then we will prove an upper bound on right tail, which will be of the same type, but will require a different proof. And then we will strengthen the right tail to the bulk, namely from right tail to bulk, right tail to bulk. And this argument will be similar to something we already did when we proved the law of large numbers, where we showed that as soon as we have a small positive probability, by truncating at the top of the tree, we were able to get an actual law of large numbers using independence of the beginning of the tree. So we will do a refined version of that. So those are the 3 steps, and unfortunately, they require a little bit of work. So that's what I plan to do. Maybe not all of today, but at least a good part of the lecture. Okay, and then last time, towards the end, I introduced the ballot theorem. So let me reproduce that here. So and the ballot theorem said essentially that the probability that Sn was greater than k, so if Sn is a random walk, and let me state it for Gaussian increments, although it is true for much more general situations. So let's write here Gaussian increments. So this between k and k plus 1, and Si positive for all I. So this probability is of the order of k plus 1 over n to the power 3/2, where this is as long as k is smaller than square root n. And actually, the upper bound is true for any k, but okay. So once we have these results, once we have the ballot theorem, let's do the lower bound. Lower bound, right tail. So if we follow the philosophy that we did when we did the law of large numbers, we saw that we can put into the events that we care about whatever we want, and as long as we can show that the second moment square is comparable to the first moment, the second moment is comparable to the first moment square, we will have some estimate. And here we have this 3/2, and as I pointed out last time, this 3/2 is somehow related to the 3/2 over here. So we can put a stricter event into the law. But before I do that formally, maybe I should explain why would we expect any change at all. So let's take the tree. So this is now heuristics. So let's take the binary tree and compare it to this situation where we have 2 to the power n independent particles, right? That's how we did the law of large numbers. Essentially, we showed that at the level of the law of large numbers, this and that are of the same type. Now, what is the difference between the two? Let's take an intermediate time. Let's call it t. Okay, so t is between 0 and n. And let's take here another intermediate time, again call it t. And now let's ask ourselves how many particles we have here and how many particles we have here. Obviously, in the left, we have less particles at time t. So at time t, we have here 2 to the power t particles, whereas in the independent situation, we have 2 to the power n particles. Okay? Now, that doesn't really matter if I'm asking about the endpoint. Because when I ask about the endpoint, the way I achieved the law of large numbers or that particular value alpha n is I compared the number of particles here to the probability of deviation. But now I have additional conditions that will come up from the fact that at intermediate points I have less particles. In particular, from this picture, I know that I must have that 2 to the power t times the probability that st is larger than a alpha n t over n. So let's write it like that. If I put here a z that is such that this total thing goes to 0, then I know that the particle here cannot reach that level. Because it's just an upper bound. It's just a first moment method for the intermediate times. So let's see what z will fit here. Okay? So I have 2 to the power t, and now it's going to be e to the minus x star t plus z square divided by 2t. I'm going to ignore the polynomial factors for a while. Okay? So if I open the parenthesis, I'll have 2 to the power t e to the minus x star square times t over 2. That's the leading term. And then I have an additional term, which is e to the minus z x star t. No t. Okay? Then the third term is going to be negligible. The z square term is going to be negligible because z is going to be much smaller than t. Now, our choice of x star is such that this product is 1. That's how we chose x star. So this means that the z you can stick in here cannot be too large. Now actually I said let's forget about the polynomial factors, but in fact if we add the polynomial factors, or the polynomial factor which is of order square root, of order polynomial, which is logarithmic in n, here you see that you cannot. So you will have something like e to the minus some constant log n. This is a polynomial. And I don't care at the moment about this constant c. Now, remember, we are looking at alpha n, so we are already going to subtract some logarithmic term. So this, in fact, the z we are taking here already will have a minus log in it. So this will become a plus log, which will kill off this quantity. But we see that z cannot be much larger than logarithmic. Because as soon as z is going to be much larger, so if z, for example, if we take z, which is larger than minus c log n, or actually larger than kappa log n, let's call it like that, then the right-hand side goes to 0, and this is impossible. So this is impossible. Yeah, but t, okay, I'm taking t to be of the same order as n. So log t and log n are the same up to constants. Okay, I'm only caring here for t between epsilon n and 1 minus epsilon n. So t is macroscopic, not microscopic, and therefore when you take the log, it's the same thing. Okay? So we see that this is impossible, and therefore what is the conclusion? The conclusion is that in branching random walk, the leading particle is always smaller than alpha n t over n plus some kappa log n. For some kappa, I don't care at the moment. At the level of heuristics, I don't care what this kappa is. Now, this is tiny. So you're essentially in this situation, because this is a leading particle, there is a linear thing, but when you are Gaussian, to condition to be large is essentially the same as changing the mean. So when you subtract what you added, at the end, you end up with a zero mean random walk that is required to be all the time smaller than this value. But being all the time smaller than this value is essentially the same as being all the time negative. It will turn out in the asymptotics. And therefore, we will pick up a polynomial factor, which is 1 over n to the 3/2. Whereas in the independent situation, we didn't have that constraint. And then the polynomial factor that will come up here is 1 over square root n, which is a probability to end up, it's a local CLT factor, the probability to end up at a particular point. So this is a big difference between the two cases, that because of this extra constraint that comes from a first moment, just a first moment consideration. Just look at intermediate time, look at the extra constraint that comes from this intermediate time. You get a constraint on the random walk. Putting this constraint on the random walk reduces the probability. If you reduce the probability, the only way to compensate for it is to move to the left so that you have a bigger probability. So that's really what is going on here, okay? So that's the heuristics. And we'll see, and I'm going to insist on this heuristics on several times. So if it didn't go down very well right now, I'll do it again, and then it will go down better. But what do we learn from this heuristics? If we are after a lower bound, this heuristic tells us that the typical event we should look for is to be all the time below the straight line leading to wherever we want to be. When we do a lower bound, we can impose it. It doesn't cost us anything. We can just say, if this is the typical behavior I expect, I'm going to do a lower bound with this event in mind. Okay? And so, let me introduce this here. So let's fix y positive. And let's define an of y to be alpha n plus y. So this is the same alpha n that I had over there. And now define AV to be the event that SV is in an minus 1 an. So the end point is where I want it to be. But SV of t is less than an t over n. Okay? So remember, SV of t was a partial sum up to time t. So SV of t was a sum over all w in 0 connects v, w smaller than t of x w. Okay, for all edges there. So this captured the heuristics I just told you. I'm asking to be all the time negative after the tilt. And then we are going to define Zn. By the way, for those who attended yesterday's exercise session, so when I refer to tilting, this is the same as saying the change of measure or the tilting in the proof of Cramer's theorem. It's exactly the same thing, and we'll see it come up again here. End of parenthesis. Okay, so we take V in the N, indicator of AV. And now we are going to apply a second moment method, just to this object. Let me erase the heuristics. Okay. So for the Gaussian situation, we had that the moment we had this, those were normal 0, 1, and then the rate function I of x was just x squared over 2, which is not surprising. So we have a Cramer's theorem for this situation. And now it turns out that everything depends on n. So we will have to do a change of measure, but somehow n dependent. So we are going to introduce a new parameter lambda n, such that lambda n times an over n minus lambda of lambda n. So lambda of lambda n, this is going to be I of an over n. So this is a rate function associated with the endpoint. So this parameter lambda n is a tilt you need. I'm writing it here in full generality. Of course, in the Gaussian case, everything is easy because it's a quadratic equation that you can solve easily. But in general, what are we doing? We are finding the tilt that will lead us to this value for the average. Okay? So that's the meaning of lambda n here when we do the Cramer's theorem. And then you will find that lambda n is lambda star minus 3 so I'm writing here in full generality. And then there's an error term. So we get we get this lambda n. And maybe I should remind you that this is just the supremum over lambda of lambda a n over n minus lambda of lambda. So the lambda n is the point that achieves the maximum in the Legendre transform in the definition of I. Okay? So now that we have found what is a new thing that we need in order to make a change of measure, let's do a change of measure. And to do a change of measure, we define a new law. I'm going to define a new law, which is define Q by d mu to dq of x is e to the minus lambda n star x plus lambda of lambda n. Okay? So this defines for me a new measure. Now in the Gaussian case, let's stop a second and understand what it is in the Gaussian case. This is a constant. This constant is just a normalization constant. The goal of this normalization constant is just make sure that the expectation of that is going to be 1 under Q. And what does a linear change of measure do in the Gaussian case? If I take a Gaussian measure and I do a linear change of measure, what do I get? Shift in the mean. Okay? So all I'm really doing here in the Gaussian case, I'm shifting the mean. So the measure Q is just the measure mu, so that the mean is shifted to be, instead of 0, it's going to be at an over n. And the parameter is n dependent because an over n is not exactly a constant. It's almost a constant, but there is this extra log n over n correction. Okay? Is that clear? So now we repeat the steps in proving a lower bound, except we are not going to care about just exponential rates. We are going to compute exactly the probability, not just the exponential rate of growth of probability like you usually do with Cramer's theory. So let me do that here. So what I'm doing now, I'm computing the probability of the event AV that is written over there. So what is the probability of AV? So mu is, by the way, my Gaussian, my original measure. So the probability of AV, I can do the change of measure, write it under Q instead of under P. What I should say is that I do this change of measure for all increments. So I'm really doing a product of these changes of measures. Each one of the variables along the way, I'm doing this change of measure. So when I'm writing Q, I don't distinguish between just changing an individual random variable and just changing all of them. So if I change all of them, what I pick up from the change of measure is this thing, or maybe SV, yes, plus n lambda of lambda n. And then I have the indicator of AV. Right? I just wrote the probability of AV, but not under the measure mu, rather under the product measure Q, the product of the Q's. And of course, on the event AV, I know what is SV. Because in the event AV, SV was constrained. It is essentially AN. So what is written here is greater than or equal to e to the minus lambda n, AN over n, no, y over n, no over n. So there's a typo in my notes. Sorry, there is an n outside. I want to put an n outside. E to the minus n now there is an n, minus lambda of lambda n, right? Times EQ of AV. Okay? This is exactly I of AN over N. That's how lambda n was chosen. So this is equal e to the minus n I of AN over N times EQ of AV. Okay? But what is EQ of AV? So now I'm going to restrict attention to the Gaussian case, although what I'm saying is going to be true in general. So under the measure Q, we are Gaussians. The random variables are Gaussians with a mean which is AN over N. So if you subtract the mean, you get again a Gaussian random walk with mean 0. So if you subtract AN over N from the increments, your end thing is to have SV between minus 1 and 0, and SV negative all the time. Because that's exactly what will happen if you subtract the mean here. So EQ of AV, okay, you understand what I mean. It's the probability of AV, it's an expectation of the indicator. This is exactly the probability that a random walk with zero increment, with mean 0 increments ends at minus 1, 0 and is throughout. So I write it in words so that it is clear, but that's really what it is. I subtract the mean. When I subtract the mean, that's what I get for the event. Okay? But for this, we have the Ballot theorem. This is exactly the event that appeared in the Ballot theorem. So this is greater than a constant divided by n to the 3/2. Okay? So now you substitute this here, and you get that this is greater than constant divided by n to the 3/2, e to the minus n I of AN over N. Is that okay? And this is going to be, if you now substitute what I is, so remember I is just AN over N square over 2, you substitute everything, you write what AN is, which I have erased. But anyway, you substitute it, and you get that this is greater than a constant times e to the minus x star y. Okay? So the first moment is of order 1, depending on y, but it's of order 1. So our next goal will be to prove a complementary bound for the second moment of this random variable. Once we have a complementary bound for the second moment, if it is of the same order, the game is over. Okay. So how will we, is it clear what our next step is going to be? Okay. So I want to apply now the second moment method. So what we have seen now, and this I will do with less details, of course, because it's a more complicated computation. But the idea is really the same. Namely, so recall what Zn was. Zn was the sum of indicator of AV. Oh, so that's, I'm sorry. I said here nonsense and nobody corrected me. So, of course, what is written here is not true. What is missing here is this is equal to 2 to the minus t, 2 to the minus n times that. Sorry. So this factor, of course, doesn't disappear. It's giving you the 2 to the minus n with these corrections. Okay, sorry about that. So Zn, which is like that, then the expectation of Zn is just greater than or equal to constant e to the minus x star y. This is a computation we just did. There are 2 to the power n particles. And now what is the expectation of Zn squared? So this is a sum over V and W. The expectation of the indicator of AV intersect with AW. Okay? Now, there is a diagonal term. And the diagonal term is just going to give me the expectation of Zn. Okay? And then I have plus what? I have the sum over V not equal to W of this expectation. Okay? But this I can split according to the time in which they split, the two particles. So I have the sum from t going from 1 up to n. T will tell me the place where they split. I have 2 to the power n times 2 to the power n minus t such pairs. Okay? So this is a total number of pairs of particles that split at location t. And then I have the probability of AV intersect with AW, and this is for V and W, such that the distance of V and W is equal to n minus t. Right? They split at location t, so the distance is n minus t. Is that clear? So that's what you get. And now, what do we have? Let's draw a picture. So now we really have a question about two particles. We forgot about the three. That's a good thing about the second moment. We just have to worry about two particles. What do we know about these two particles? They move together up to time t. And then they split into two independent objects. This guy and that guy. And now it's again a computation, not much more complicated than what we did before. You can condition on the value at the splitting point. Okay? Compute the probability to start at 0 and at this conditioning value. So maybe I should write it. I should write one more line, and you can guess that I don't want to complete the computation. So I'm going to write the probability of AV intersect with AW to be the expectation of the indicator of AV intersect with AW conditioned on S where A of VW is the ancestor of V and W. It's a common point. Okay? And then you see that it decomposes into three ballot events. The first event, first of all, the value at the ancestor cannot be positive because of the constraint we have inside AV. So remember, everything now, we can again do everything under the measure Q. No problem. When we do everything under the measure Q, we come back to zero mean random walks. And under the measure Q, this S has to be negative, non-positive. And so you just sum over all possible values of this intermediate point, and you apply the Ballot theorem actually 3 times. Once for the interval between 0 and that intersection point, 1 between the intersection, and then squared between this intersection point to the end. So this I want to skip. The details are in the notes if anybody is interested, but I don't think I want to put more time into that right now. And when you do that, you will see that this is greater than, this is less than. Now we need an upper bound, not a lower bound. This is going to be less than a constant times e to the minus x star y. And in fact, the interesting thing is, and this is something to keep up in mind, when you do that, you can look at what is the intermediate value that is going to contribute most. And as it turns out, it is not in your advantage to require this point to be at 0. So after the change of measure, remember, we want to be negative for the whole way. We want to be at 0 here. And you can ask the question, what is the most advantageous value in the intermediate point? So the answer is, it should be of order minus square root n. That's the typical order. If you ask this intermediate value to be near 0, you will pick up an extra factor of 1 over n to the 1/3. And that's going to make the contribution of that small. So the main contribution here is going to be coming from just taking a typical path, which essentially is like that, where the distance here is of order, it's a random variable, which is of order square root n. That will turn out to be the leading contribution. And everything which is larger than order of square root n is going to be completely forgotten. And in doing this computation, one can use the fact that in the Ballot theorem, in fact, you have an upper bound that is valid for any value of k. In the lower bound, we needed k smaller than square root n. The upper bound is valid for any value of k, and that's what you get. Okay, so you get from this type of computation this upper bound, and therefore you get that the probability that Zn is greater than or equal to 1 is greater than the second moment square divided by the first moment. So it's, it's the expectation of Zn square divided by the expectation of Zn square. And this is going to be like that. Okay? And in particular, this is, if this were the correct tail, this would be integrable to the right, but we are not dealing yet about that. Questions about the lower bound? So I should say that the idea here is following Bramson's proof, although he has not really written it in these terms. And however, there is a simplification. So this is following So Bramson used a more complicated event for AV. He wrote it in a different way, but his proof amounts to looking at a more complicated event for AV. And Matt Roberts recently pointed out that, in fact, you didn't need to look at complicated events. This is quite sufficient. Okay, so that's a lower tail. And usually, the lower bound is a harder one, because for the lower bound, you need a second moment. For the upper bound, in principle, a first moment is enough. Now that would be the case here, except that if you do a first moment, you get the wrong answer. Right? Because the first moment does not distinguish between the dependent and the independent case. So you have to do something else for the upper bound. And so, in the upper bound, let's think about what is going on. So that's a second step of the proof. So we want to do an upper bound for the right tail. And the intuition we have, which is the intuition that guided us into the lower bound, was to say, well, we have to constrain the walk not to go above a certain curve, because this is impossible. So we have to take that into account somehow. So let's split the event we care about into two. So introduce the curve. So I hope this picture is clear. You take the log up to n half, and then you do a symmetric reflection on the other side. Okay? So that's a function kappa log t. And we know that it's unlikely to go above this curve. Of course, it can happen in the beginning. And it can happen in the end. But we saw that in the middle, it's absolutely unlikely to go above this curve. Yes?
What's the difference with log t?
Kappa. So some constant, the same constant kappa that I don't want to specify it because it plays no role. So fix a kappa large enough, it has to be, I think it has to be larger than 3/2 or 3/4 or something. But some kappa, which is large enough. And it's the same kappa that you need to ensure that in the middle you don't go above this curve. That's all you need. Okay. So before I do the analysis of that, let's think for a second, what would I do if I took a curve like that, the red curve, kappa log t. Then I would say the probability that there exists a v such that SV, a v in the n, such that SV is larger than an plus y, this quantity, this would be smaller than a union of two events. The first event is that there exists a v in the n such that SV of t is larger than kappa log, not log t, log n. Kappa log n for some t. Plus the probability that there exists a v in the n such that SV is greater than an plus y, but SV, sorry, this is not, but SV tilde of t is less than kappa log n for all t. So let me explain. What is SV tilde? SV tilde is just SV when you subtracted the mean. So SV tilde of t is just SV of t minus an over nt. Okay?
Do you mean kappa log n or kappa log t?
Well, here?
Yeah.
No, kappa log n. You see, at 0 it is not at 0. If it were kappa log t, it would drop down. This is a curve kappa log t. So I'm doing first a heuristic explanation when I replace this fancy curve h by just the red one. and I want to explain what is going on in that case. Okay? So this is certainly an upper bound. This is a perfectly legitimate upper bound. I'm saying either you end up high by crossing the red line or without crossing the red line. Now this, we already showed, goes to 0. Because we showed you cannot cross a line which is kappa log n because of the constraint, because of the first moment. So this will go to 0. Okay? What about the second guy? Well, this is exactly tailor-made in order to apply the Ballot theorem. So this is, now you can do a first moment method on this second guy. So this is smaller than 2 to the power n, the probability that SV is greater than an plus y, but SV tilde of t is less than kappa log n for all t. And this would be almost good. This would be almost good, except for one problem. The log n that I have here, so this will turn out to be less than log n times a constant. Because in the Ballot theorem, we have, remember what was the Ballot theorem? It had the height divided by n to the 3/2. The numerator had the height in it. So you will end up with a factor log n here, which is not giving you quite an upper bound. And if you wanted to correct for it, you would need to push in the an to add a log n correction. But we want precision up to order 1, so we cannot allow log n terms. So instead of doing this red curve, we have to worry about what happens also in the beginning and in the end, and that's the reason why I put this curve h of t. Okay? And this makes the proof slightly more complicated, but there's a nice trick that will come. So let me try to recapitulate that. The first thing you guess in doing from the constraint I explained in the beginning, you put a constraint here. You split the event as the event of crossing the constraint or not. And unfortunately, when you do that, you miss by a little bit. You get something which is logarithmic as the upper bound in the expectation. And to correct for that, you would have had to switch things further to the right by a log n correction. So that's not quite good. So we are putting this h of t. So now actual proof. So this was Juris, this was attempt 1, which almost worked but not quite. And then the attempt 2. By the way, I say it almost worked but not quite, but it would already show, if all you cared about is to know the order of the logarithmic correction, it will already give you that. It will already tell you that the correction is 3/2 log n plus maybe a log n. So the second attempt is to use the curve h of t. But now what you need to do is to introduce tau of v to be the first time that SV of t, or maybe I will use just SV tilde, is greater than h of t plus y. So you go above the curve by a fixed amount, and the right amount is t. So SV tilde is again the shifted one, so this can be written as SV greater than an over n times t plus all this junk. Okay. So now we are going to try to do that, except that it is not unlikely to go above this curve. Because in the very beginning, we agree it's very unlikely to go above this curve here. But it's not particularly unlikely to go above this curve in the middle. That may happen. Okay. So how do we deal with that? So, so now we there are two steps. First step is, let's pretend so step one. In the first step, we're only going to worry about particles that do not go above the curve. Okay? So only worry about particles that stay below curve. So what does that mean? We introduce the event BV, which is the event that SV of t, so SV tilde is less than h of t plus y, and SV is in an minus 1 an. This is for all t, this is like that. And now the claim is that the probability of BV is bounded by a constant times y plus 1 squared e to the minus x star y times 2 to the minus n. This is a claim. The proof is again a change of measure. So, but there is one little twist that I want to very briefly mention. So the proof. So again, do a change of measure. But you see, now the natural change of measure is not one that will make the mean 0, but it's one that will make the mean on the curve. If we want to use the Ballot theorem, eventually we have to make the mean on the curve. So use change of measure with independent but not IID increments where the parameter chosen to have mean so it should be an over n plus beta beta t, and beta t is simply simply h of t minus h of t minus 1. So you want to achieve a total partial sum which is a log t. So in each increment, you just make a change of mean which will correspond to the value you want to achieve. So now you do the same computation as we did before. What will you get? You will get eventually an event which looks like a Ballot event. Namely, you want to end up at a point and be all the time negative. But you will have an extra factor coming from the change of measure of these guys. So you do that and then control the contribution of the beta I to the change of measure. And what turns out to be important is that the sum of beta I. So for this control, what you will use is that the sum of beta I is 0, but the sum of beta I square is a constant, is bounded by a constant. Beta I is roughly 1 over I. But it's, because it's a curve like that, it increases and then decreases back, so the total sum is 0. So the total sum of the beta I does not contribute, but the sum of beta I square is the sum of 1 over I square, so it's finite. And these two facts, plus an integration by parts, or a summation by parts, allow you to control the exponent in the change of measure. Okay? So I don't want to do this part. The details are actually in the notes, so if anybody cares to see the exact details, you can see that then. So that's the first step. But that's not all. Now we have to think about how to handle the case where you do cross this line. And here is a nice trick for doing that. So define now So by the way, if this is a probability of BV, then you see that the expected value, so if you define now Yn to be the sum of the indicator of BV, you see that the expectation of Yn is bounded by a constant times y plus 1 times e to the minus y x star. So in particular, it's integrable. So the right tail is integrable, and therefore the probability that one of them occurs decays like that, and that is good enough in order to conclude integrability of the mean, except that we have not taken care of the event that we could go over the line.
You mean y plus 1 squared?
Sorry?
You mean y plus 1 squared?
Here? Yes, thank you. Thank you. the same quantity that we get there, yes. Okay, so that's the expectation of Yn. And now remember, now introduce the time tau. So where was the time tau? So let us introduce the time tau. So second step, step 2. We need to worry about going above the line. So introduce the first time that we go over the line. So let's call it tau. So tau of v is the first time that SV of t is above h of t plus ant over n plus y. That is tau v, and tau is the minimum of tau of v. So it's the first time that there is a particle that goes above the line. And now, let's compute. So the expectation, so what, so this is a fact. This is greater than a constant. So everything has been designed, so let me explain what is going on here. So remember, in principle, when we did the lower bound, we had an estimate that decayed with y. But I claim now that no matter what y is, the expectation of Yn is actually larger than a constant, a true constant. And why is that? Because the fact that tau is less than n means that there is some time in which you have a particle that is above the line, starting here. So now just look at the descendants of this particle. These descendants, they start very high. They start at a height y, or actually larger than y. And so we apply the lower bound to them, For them, they just have to be above 0. There's no issue of climbing y more. They just have to keep their height. So we got rid of the factor y, and therefore the same lower bound that we already did applied to the single particle that crossed the line will show you that this expectation is bounded by a constant. Okay? Because we are already starting high. The point is that you have a particle that already, on the event tau less than n, you already have a particle that started high. And if it started high, it's as if I added this starting value to whatever computation I did before. And that will take care of y. Yes?
What is yn?
Yn was defined, it's just the sum of the indicators of BV.
What if BV was then, how can tau happen? If tau happens, then BV doesn't happen, right?
Okay, so hold on. So this is V in dn. And in fact, you are right. So this should not be yn. I'm sorry. Excuse me just a second. You're absolutely right. You are absolutely right. Yeah, so what I really should have here is not BV. What I really should have here is just
This BV is from the step 1.
Yeah.
So that's fine, I think.
You should modify it to some CT or something.
no. Why is it fine?
No, it's not.
No, I don't think it's fine. This is true that here I'm not allowing myself to be above this line. So it's probably not BV, but actually it's actually the event, yeah, so it's not well written. It's actually the event that you end up, so it's probably not yn, but rather what I call zn, that you end in the right location, okay? So also it's not yn. That you end in the right location. But no, there is something that bothers me. Excuse me just a second.
Maybe this is on the event that tau happens. In the event that you actually get above it.
It's not the end. Because the end has BV.
I'm sorry, it is yn and there is no problem. Sorry. The fact that there is a particle that went above the line doesn't mean that there cannot be other particles who do not go above the line.
Oh,
Yn is just the sum of all, I'm sorry, I got confused here. So Yn is just this sum. This sum is well defined. The fact that there is a particle that goes above the line, no problem at all. Okay? Is that? So was this discussion clear? I'm sorry, it threw me off, and I'm afraid I confused many people here. So remember what Yn is. Yn is just counting how many particles remain below the line for a long time, for the whole trajectory. And arrive at the right point.
I don't see why then if one goes over the line, I don't see how this increases.
Because BV is just looking at each individual particle.
Yeah, but I don't see how the conditioning helps. Yeah.
Ah, wait, I didn't say it helps. For the moment, the argument was, the discussion was, if this event happens, then Yn equals 0. And that's not true. Okay? You'll see in a second why it helps. It's kind of, it's weird, but it will help. Okay, so there is no contradiction. This event does not imply that Yn equals 0, because there is just one particle that went above the line. Okay, so now we write a sequence of inequalities. So, the probability that tau is less than n, I can write it as follows. I hope that everybody agrees with that. So this is, of course, smaller than that. Therefore, the expectation of yn is larger than the expectation of yn times this indicator. Therefore, this probability is bounded by that form. Okay? But this is equal to the expectation of yn divided by the expectation of yn conditioned on tau less than n. Yeah. So maybe I should explain, maybe my explanation here, I now realize what threw you off. My explanation here was confusing because I said I have one particle that crossed the line and therefore its descendants are going to be okay. Then that is not quite true because if this particle crosses the line, it is not going to contribute to yn. However, the father of this particle is going to contribute to yn. Because the father of this particle, just a second before branching, before going over the line, there is someone who is just below the line. And that someone is going to have children who end up in the right height. Okay?
The brother of this particle.
The brother, yes, right. Or maybe the cousin or the second cousin, but one of the close ancestors of this particle is going to be. That's absolutely right. Good. So, okay, but now we are done, right? Because this, if you believe me that this is greater than a constant, then this is less than some other constant times the expectation of yn, which we worked very hard to prove that is bounded by y plus 1 squared e to the minus x star y. And that's this probability. So now you just sum the two. So now you're done, because you have this probability, which goes to 0 with y. And then you have on the event that this did not occur, we had the expectation of yn fine, so everything is fine. Okay? So that's the second step in our proof. So where are we? Let me recapitulate where we are. So what we have shown so far is that is of the order of, so is greater and smaller than e to the minus x star y. And for the upper, either a constant, so greater than a constant, and lower than y squared. So I hope it's clear what I mean. The lower bound is a constant multiple of that. The upper bound is y plus 1 squared times that. So we have an up and a tail on the right side. Now already this estimate implies that the expectation of mn is bounded by an plus a constant. Right? So actually this was alpha. So, well, alpha n was. So this is where we are. So we have an upper bound on the expectation. We need a complementary lower bound on the expectation. But this is going to be very easy, in fact. So I'll just draw the argument and not write too much. So again, we are going to cut the tree at the depth L. L is going to be of order 1 fixed. And now we have independent guys here. And each one has a probability that is written here to be larger than what is written. Namely, each one of these guys has a probability Pn, which is a probability that n minus L is greater than an minus L. This probability is just going to be greater than a constant. I just take y equal to 0 here. Okay? And so we apply what we did before. Namely, we have a good upper bound on how big this can be. This cannot be more than a constant time L. So if we go depth L, we lose the constant time L in the value. But then the probability becomes 1 minus c to the power 2 to the power L. So the probability that all of them fail goes like that. So we went a distance L, but the probability to fail goes very fast to 0 to the power 2 over, with exponent 2 to the power L. And on the event that you did not fail, well, one of these guys is going to be alpha n minus L, which is only L away from the value I care about. And then this guy is again at most L away from 0. So on the total, I will find out that the probability that Mn is greater than An minus some constant times L decays fast in L. So 1 minus this probability decays fast in L. And in particular, it decays in an integrable way. So this will give you immediately that the expectation of Mn is greater than An minus a constant. Okay? So this is again, right tail implies behavior, which is using the tree structure. Okay. Questions about this argument? Okay, so I'm sorry for this somewhat technical. I wanted to go once over that. I promise not to do it again. So I will avoid doing this type of technical computations again in the next 2 lectures. What I want to do next is to give some extensions of this result. But before, let me recapitulate what we had. So what have we shown? So we have shown Mn, the expectation of Mn is x star n minus 3 over 2x star log n plus order of 1. And Mn minus the expectation of Mn is tight. This is where we are now. Okay. So now some general comments. So the first comment is that you can have another route to tightness and that route is actually our proof of the expectation gave us much more. Our proof of expectation, so control of expectation, actually gave tail estimates. Right? We had an exponential tail on the right. If you carried out the proof of the lower bound, the right tail to bulk proof, it will also give you an exponential tail. So that's okay. So we have a control directly. So in fact, we didn't really need decking and host. We could have proved the tightness without using at all the argument of decking and host. That's the first comment I would like to make. The second comment is that in fact there is a third route to tightness. Can use a certain recursion that holds for the distribution function. Namely, if you define fn of x to be the probability that mn is less than x, then from the tree structure, just cut at the first generation, you get that in order to be the maximum to be smaller than n, you get the equation that fn plus 1 of x is equal to fn convolution with g square. Well, I hope it's clear what I mean here. Right? It's a distribution of mn convolved with this extra guy. So in order for the total maximum to be smaller than x, you need both these guys to be smaller than n, so you get this functional recursion. And you can analyze this recursion, and you can deduce from this tightness. And this has several advantages. I'm not going to describe that at all, but I want to emphasize that this has several advantages. First advantage is that this can allow a G which is Gn. In the analysis, it turns out that all you need is some tail estimates on G, but you don't care about whether they are similar. In particular, you can get tightness in situations in which computing the expectation of the mean is going to be tricky, because it varies too much. So this is better in some situations. It's much more complicated, though. And the second point for which this is better in some senses is that if G has a log concave density, if G has a log concave density, it turns out that you can look at Fn shifted around its median and develop a fixed point argument. So Fn of x minus the median of Fn will satisfy the similar equation, and you will get a fixed point argument which will lead to convergence. So in fact, you get more than just tail estimate. You can actually show convergence. And this fixed point, however, uses very strongly this assumption. So it's a structural assumption on the increment, which is satisfied in the Gaussian case. Okay? So for the Gaussian case, I'm sorry to break the news to you, but for the Gaussian case, everything I did here is essentially superfluous. You could get a much better result by completely analytic methods, forgetting about probability, first moment, second moment, and all that. You just look at this equation, and from the analysis of this equation, you can get all the information you need. Okay? Of course, I'm not going to emphasize that too much, because this does not generalize well. In particular, there is, first of all, it uses very strongly the fact that this is equal. So if you have approximate equalities, it's very hard to push them through. And second, it requires a structural condition, which as soon as it fails, it breaks down. So I'm not going to emphasize that, but I should maybe say that, first of all, the fact that there is a fixed point, this goes back also to Bramson's original work for BBM, and to Bachmann for the generalization I mentioned here. And then the fact that you get tightness without structural conditions is contained in a paper of Bramson and myself a few years back, and I'll say something about it in the last talk. Okay, so that was one side remark. The second side remark I want to make is related, still about that. A proof of convergence of Mn for general branching random walks. This was done recently by Adicon. So it's pretty recent. So by convergence, I mean convergence in law. And the techniques are different from what I described today. So, okay. So that's essentially the state of the art in terms of branching random walk, in terms of this kind of questions. The other thing I want to mention about about this type of classical branching random walk is you can ask now questions now that we know about the maximum, roughly where the maximum is. And if you believe me that the law of the maximum converges, you can ask questions not about the maximum, but rather, let's draw a picture. This is our point AN. So what we know now is that there will be somewhere a particle, somewhere around AN in a random location, there will be a particle. But in fact, there will be many other particles. Okay, if this is a maximal one, there will be more particles, and it's not very hard to convince yourself that the deeper you go, the more particles you will see. You can see that even from the lower bound that we did. So you can ask a question about this point process. How does this point process look like? We have this collection of points that are spread out on the left side of the leader, and you can ask how do they look. So I want to make two comments. The first one is, let's go back to the tree. If you can ask yourself the following question. Suppose that this particle is a leader. Okay? What can you say about the brother of that particle? Well, the brother of the particle is likely to be large also, because how did this guy come to become a leader? It had to more or less follow this straight line. This we know from the upper bound. So more or less it had to follow the straight line all the way and therefore one step before the end, it had typically to be pretty high, and therefore the brother, even if the brother is typical and not extremal, it will be roughly at this height. So the brother of this particle is going to be not far behind, so this guy will have a brother somewhere here. Maybe this guy is the brother of the leader. And the same can be said about the cousin, right? If you take here a cousin, then the cousin is likely also not to be too far behind. On the other hand, what about distant relatives? So what about, say, at halftime? So from the analysis we did, what do we know? We know already that the leader looks essentially like, after you subtract the linear tilt, how does it look like? It looks like a Brownian bridge. It looks like someone that starts at 0, ends at 0, and has to be negative all the time. This was the heart of our argument, that in fact this is a true behavior. So where was the leader at time n-half? Where was the leader? Minus root n, right? Because that's a typical behavior of a branching, of a Brownian bridge at time n-half. So it's unlikely that a relative of the leader, a distant relative of the leader, made it to the front, because the guy that was a leader here, okay, or the other guys here, they are not related to this leader. And in fact, you can show that the following happens. If you fix a big neighborhood here, so you fix a big K here and a big K here, then the relation between all the points that you see near the leader up to a distance which is alpha of K is that either they belong to the same clan, defined as this, or they split in the prehistory, very early on. And the reason is that it's too hard for two particles that split here. So if you have two particles that split here, it's very hard to have a leader both here and here. The probability of that is essentially negligible. You can prove it by just doing the upper bound that we did. And so the process that you see at the end is going to look like that. You will have clans, and then in each clan we can define the clan leader, right? And then you have the clan leaders that split way in the beginning of history. Now, if they split way in the beginning of history, they should look like Poisson, because they are independent. They're essentially like extremes of many independent particles, so they should look like Poisson. And indeed, this is a theorem. So the theorem is the point process looks like a decorated Poisson. So what I mean by decorated, if you take the clan leader, the process of the clan leaders is a Poisson process with inhomogeneous rate. There are more and more of them as you go left from the leader. And to each clan leader, there is a whole family around. Okay, you can now think of whatever sociological picture you have in mind when I say this sentence, but I have a very sharp picture in my mind. Anyway, there is a clan leader, and there is a whole entourage of that clan leader that is trailing behind, and like here, maybe this is a clan leader, maybe those are his family members, and then here is another clan leader with its own family members, etc. And one can describe the law of this decoration. And this, there are two groups who did this. So one is Arguin, Bouvier, and Kistler. And the other is, so here it's Adecon, Brunet. I remember Xi Chi, and I'm missing someone. Berestiki. Yes. Oh. Okay, so, and those are both relatively recent works that describe completely, you can get a complete description of this point process, and the methods that are needed to handle that are related to the spine methods that method that Pascal is going to discuss today in the exercises. Okay, I'll stop here. What the plan for next time, for tomorrow, is to pick up this model and discuss a variant of it, at least briefly, in which the increments are not homogeneous, and I'll try to convince you that interesting phenomena happen. In particular, I'll show you some phase transitions and some somewhat surprising behavior, which we will be able to analyze without too much difficulty. And then we'll switch to Gaussian free field. Okay, that's it for today.